We'll finish up this unit with a little more about altitudes and medians of triangles and how they come together to form an orthocenter or a centroid, and then also some stuff about triangle inequalities. You'll want to trim off the sides of this paper when you're done so you can fold it. First, to reiterate what we already kind of talked about, the median of a triangle is a segment from a vertex to the midpoint of the opposite side. The three medians of a triangle are concurrent, meaning that they come together in a single point, and that point of concurrency is called the centroid, and it is inside the triangle. We haven't talked about this yet, but there are some points of concurrency that meet up outside of a shape. The centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. So knowing that AP is 2/3 of the way from A to E, and that AP equals 4, you could use that information to find PE and also to find AE, as we've already practiced some in the ALEX assignments. So an altitude of a triangle is the perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. In this triangle, the altitude goes down to the opposite side as a perpendicular. Over here, this is the triangle, QPR, and then if we were to make an altitude, it would go from the vertex straight down because it's got to be perpendicular, and so this point would actually be outside of the triangle. The lines containing the altitudes of a triangle are concurrent, meaning again that they come together in a single point, and that point of concurrency is called the orthocenter of the triangle. As you can see here, the orthocenter could potentially be outside the triangle. Not every triangle is going to have an orthocenter inside. Centroid examples. In triangle RST, point Q is the centroid and VQ equals 5. Find RQ and RV. Okay, so Q is the centroid and this line is 5. Find the length of this line and of the total line. So remember, the centroid is 2/3 of the way. So this is 1/3. That means that this, which is 2/3, is twice as long. So this is 10. So that's RQ. And then these two together would be the total RV. So RV is 10 plus 5, which is 15. Find the coordinates of the centroid of ABC with vertices 0, 4, -4, -2, and 7, 1. So step 1 here is going to be to find the midpoints. Step 2, connect to vertices. And 3, find the point of concurrency, which is the centroid. So finding the midpoints, we're just going to calculate by using these coordinates here. Remember, the midpoint formula is x plus x over 2 and y plus y over 2. In this case, we've got 0 plus 7, which is 7. So that would be at 7 over 2, or 3.5. And then 4 plus 1, which is 5, divided by 2 is 2.5. So the point would be at 3.5 on the x, 2.5 on the y. So right about there is one of my midpoints. Then between here and here, this is at -4 and 0. So -4 plus 0 is -4, divided by 2 is -2. -2 plus 4 is 2, divided by 2 is 1. So -2, positive 1 is my midpoint for this side. And then here, from -4 to positive 7 is, -4 plus 7 is 3. Divided by 2 is 3 over 2, or 1.5. -2 to positive 1, -2 plus 1 is -1, divided by 2 is -1/2. So I've got 1.5, negative 1/2. That is my midpoint for the third side. Next, we're going to connect each midpoint to the opposite vertex. So just draw a line from each midpoint to the corner that is opposite to it. And they should all meet at one particular spot. In this case, they very clearly did. They all meet at 1, 1. So that's my centroid. Centroid was 1, 1. Now, finally, some orthocenter examples. So find the coordinates of the orthocenter for ABC with these vertices. So there's 3 steps to this process as well. 1, find the slope of each side of the triangle. 2, find the opposite reciprocal, because we're going to find a perpendicular line. And 3, use point slope form, y minus y1 equals m times x minus x1, to use the perpendicular slope and the point, that's the vertex, to draw our altitudes so that we can find the orthocenter where they cross. For this one, we're going down 6 over 6. So that's a slope of negative 1. Our perpendicular slope would be positive 1. And we're going to go through this point right here. So I'm just going to draw a line with a slope of positive 1 going from 1, negative 6 to this side. So it's going to go up 1 over 1 all the way over until it meets that side. And I could do some more math and show some more work for this, but there's not a lot of room on here, and I can just go ahead and draw it like this. Next, I have this side, which goes up 2 over 6. So up 2 over 6, that's 1/3, a slope of 1/3. So my perpendicular slope is going to be negative 3. And I'm going to go from this point, negative 3, until I meet this. So down 3 over 1, down 3 over 1. And we can see that right here it actually crosses the other line that I drew. So I'm going to go ahead and make that my point that I draw from. Go through the other side. And remember, both of these are perpendicular lines. So they are forming right angles with the opposite sides. And finally, the easiest one, I say for last, this is an undefined slope, but the perpendicular slope would be a horizontal line. I know it's a horizontal line going straight through this point. So all I got to do is just draw a straight horizontal line across, because that would be perpendicular to my vertical line. It's going to go across and go through my point over here. And again, this is a right angle, of course, to this side, but clearly my orthocenter is right here. Orthocenter is at 3, negative 3. Next, find the coordinates of the orthocenter of DEF with these vertices. I'm going to do the same process. So this is a slope of up 8 and over 4. So that's a slope of positive 2. So my perpendicular slope would be negative 1/2. So this is the vertex that's opposite this, and my slope is negative 1/2. So I'm going to go actually like this, down negative 1/2 to get to here. So we're going to go back 2, up 1, back 2, up 1 a couple times just so we have something to draw to. And then we'll draw our line going way off over here. Like that. So this orthocenter is clearly going to be somewhere outside of the triangle because I'm already outside of the triangle. Next, I've got this slope, which is up 8 over 8. So my slope is 1, so my perpendicular slope is -1. And this right here is my opposite corner, so I'm going to draw a line with a slope of -1 right through there, going all the way up to where it connects with this other line. Again, this is forming a right angle with this side of the triangle. If this line continued on, it would be a right angle here as well, but it's outside the triangle entirely. And then finally, my final altitude is my easy one. This is a horizontal line, so my perpendicular one is going to be vertical, and it's going to go through this opposite corner right here. So it's just going to go straight up and down over here. From there to where my other 2 points already meet. And there is my orthocenter at -410. Okay, next we have this foldable, which we're going to cut around the side of the square and then fold in. So once you've folded it up, it'll look something like this. First, I'm going to turn it over. I'm going to write this on the back side, but you should write this in your notebook because this is the side you're going to use to glue. So this is the triangle inequality theorem. And again, this should go on the notebook page next to where you're putting this. The triangle inequality theorem. The sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. In other words, if I add up any 2 side lengths in a triangle, I'm going to get a number bigger than the other side. If I don't, then it's not possible to make a triangle with those 3 side lengths. So as we look at these examples on the other side, we'll see some of the ways that that works out. So first, is it a triangle? So let's determine whether we can even tell that the following sides could form a triangle based on the triangle inequality theorem. So we'll usually start by adding up the 2 smallest numbers, and if they're not bigger than the biggest number, then we know we don't have a triangle here. So in this case, 8 plus 17 needs to be greater than 24. 8 plus 17 is 25. 25 is greater than 24. So yes, this could form a triangle. Here we've got 3 plus 3. We need that to be greater than 7. 3 plus 3 is 6. Is 6 greater than 7? No. So these could not be the sides of a triangle. Then we've got 41 inches, 7 inches, and 35 inches. So again, the 2 shortest sides are 7 and 35. We need 7 plus 35 to be greater than 41. 7 plus 35 is 42, which is greater than 41. So yes, this one could be a triangle. We can also use this theorem to find a range of possible side lengths. So, for example, if I have 2 sides of a triangle given as 3 and 11, how big would the third side have to be? What's the range of possible lengths for it to be? So I know that I would have to be able to add these up and have them be greater than my third side, however long it is. And 3 plus 11 is 14. So x has to be less than that. I also know that if I add 3 plus whatever my third side is, what I get has to be greater than 11. So if I solve this for x, subtract the 3, that means that x has to be bigger than 11 minus 3, which is 8, which means that x can't be any smaller than 8, and it can't be any larger than 14. It can't equal either of those either, so it's got to be bigger than 8 and smaller than 14. Same process here. I know that 28 plus 31 is 59, so that's the biggest. My x can't be bigger than that. And 31 minus 28 is 3, which means that x can't be any smaller than that. That's a pretty big range, but anywhere in there would work. Anything bigger than 3 and smaller than 59 would create a viable triangle here. And then 24 plus 7 is 31, so it has to be smaller than that. And 24 minus 7 is 17, so it has to be bigger than that. So it has to be between 17 and 31. Now this is an important principle that we've kind of discussed briefly a few times, but the smallest angle is always opposite the shortest side. And this makes sense when you think about it, because the angle is a measure of how wide this opening is, right? So if it's a narrower angle, then it's going to be a narrower side. If it's a wider angle, then it's going to be a longer side on the other side. The largest angle is always opposite the largest side or longest side. So if we were to order the angles from least to greatest here, the smallest angle is going to be across from the smallest side, which is 17. So that's angle C. And then the next smallest side is 20. So that's angle A. And then the longest side is 24, which is across from angle B. So that must mean that angle B is the largest angle. Obviously, the opposite is true as well. The shortest side is always opposite the smallest angle. And the longest side is always opposite the largest angle. So we can use that to put the sides in order from greatest to least as well. So first of all, I don't have a third angle, so I need to use Pythagorean, or I need to use the principles of triangles to find it. So I know that these add up to 180. 59 plus 53 is 112. 180 minus 112 is 68. So this is 68 degrees. So D is actually my largest angle. That means that EF is my longest side. Next largest angle is angle E. That means that DF is my next largest side. And finally, my smallest angle is 53 degrees, angle F. That means that DE is my smallest side or shortest side. And finally, make sure you grab one of these papers. Just really briefly, Hinge theorem is if two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, then the longer third side is across from the larger included angle. So if I've got two triangles that have equal sides, two equal sides, but the angle in between them is not the same, then that means that if this angle is bigger than this one, this side is longer than this side. So it's a really obvious thing to conclude from what we were just talking about, how the longest side is always across from the largest angle.